Okay, everybody, good afternoon. I'm happy to be here, and I think that we all need to thank Nir for the marvelous conference. We don't need to take any airplane or even a train. So today I will tell you some stuff that we are doing here at the Technion, mainly related to hysteresis in carbon nanotube field effect transistors. And this is a very elaborate work done by many students, postdocs, lab engineers, and also faculty. So just before I dive into the main topic, I just want to tell you a little bit about our research interest. It's related to electrical and chemical sensors based on these materials. This is like suspended carbon nanotubes. Another one, this is like AFM image, SEM image. This is like force of carbon nanotubes with different densities. You can use it for supercapacitor, thermal transport, solar energy. You can create like nanofluidics with this forest. You can create fins. You can create like tube inside tube, holes. Here you have a graphene membrane. Of course, you can use it for MEMS applications. And you can use this structure for filters, nanofluidics, 3D structures, many, many things. But today, I'm going to tell you about something very, very specific, and you will see soon. So, this is like in the last 15 years probably, there's a huge amount of research in the field of carbon nanotubes and graphene. And for example, now I want to focus on electronic applications. So this, for example, is a work that was done recently from the Stanford group. It's like the first carbon nanotube, only carbon nanotube computers. Okay, so it's really many carbon nanotubes that behave as computer. This is for example, sorry, going the other direction. This is, for example, a graphene nanoribbon. So the idea that graphene doesn't have a band gap, so you make them very, very thin. Practically, you behave like a carbon nanotubes, and then you can think about this will be our channel, will behave like a field effect transistor. This, for example, like a spin-off company of Harvard that create like a memory unit from carbon nanotube that can stick, go up and down, and create some memory element. So everything is very nice. And it's very promising. And I think that the beauty of carbon nanotubes is first because they are like open configuration, high surface to volume ratio, 1D system, so it's really perfect also for a channel behavior and also for sensing application. But the main problem, which really always exists, and usually nobody really wants to deal with it, is the fact that if you look at the transfer characteristics, I as a function of gate voltage, always there is some hysteresis. And if you want to do some real electronics, you cannot really deal with such hysteresis. Even if you want to use it for like a non-volatile memory, it's all the time going to be different what you expect, okay, because it depends on many parameters. So it's really a big, big problem. Moreover, if you think about sensing application, which is like the main issue of carbon nanotubes, so you can put yourself, let's say here the transconductance is very high. You would like to be there for sensing application. Then when you look at the current as a function of time, you see that it's decay, meaning that practically the transconductance can be much lower when you're going to do the experiment. So this is a real problem. Nobody, I think that, I knew about this many years. I never wanted to deal with it, and we wanted to do something completely different, but when we start doing something completely different, we understood that we must understand this problem much better. So what people thought? People thought about a defect in the carbon nanotubes that can cause this hysteresis. People thought about mobile ions on the dielectric, and I will turn back to this hypothesis. People thought about mobile ion within the dielectric. There are many problems with all these scenarios, and I'm a little bit just quickly tell you about them. There could be some charge injection into the bulk. If this is carbon nanotube, there's a very, very high, strong electric field, so you can have some tunneling from the nanotube back and forth that create this hysteresis. And I think that roughly what the community came out about is that you have this hysteresis is really related to like you have like surface traps, and the electrons are really going back and forth the carbon nanotubes, and it's related to humidity. You must have humidity or some water layer that exists in the environment that enable this tunnel behavior between the movement between electrons back and forth in the carbon nanotubes. And it was very nice. It was a very nice experiment in the group of Fungi Dai from Stanford that he showed, let's take a carbon nanotube which is suspended. And then you say, okay, we don't have any surface. But still you see this hysteresis. So how come? So they say, okay, let's say think about the carbon nanotube. It has some water layer on top of it, and then there's some resistance between the water layer and the carbon nanotube. This acts like a resistor and a capacitor. You have some RC circuit, and you get this hysteresis behavior. And practically, I can tell you that it's really quite weird because carbon nanotubes are hydrophobic. So why really water would like to stick to carbon nanotube? So, what people know, if you look at this cartoon, this is our carbon nanotubes, and it's not really perfect as we think. It leaks, and we cannot do many things that we would like to do. And personally, me as the one that studied this carbon nanotube and liked them very much, I felt insulted for this carbon nanotube that people call them leaky transistor. But we decided to do the following. If they are really leaky, so it should be some way to measure this charge. Because charge is going back and forth, so we'll be enabled to see this charge. So how are we going to modify to see the charge? The idea was by using like a surface probe. The surface probe is like EFM, electric force microscopy. And the idea is the following, like it's a very sensitive tool. The first scan just take the topography of the system, of the surface, and the second scan at a given height can sense really the electrostatic force. And from practically what it sends the derivative of the force, and from the derivative of the force, you can extract, if you have a nice model, you can extract exactly the landscape of the potential. So this is how it's done, for example. This is the deflection, a function of distance. You come, you approach, and you go up. You can see, you can measure the deflection, you can measure the amplitude, you can measure the phase. So here, for example, everything is made here in the Technion. This, for example, our carbon nanotube. This is like a suspended carbon nanotube AFM image. When you come on with AFM, it's moving a little bit. This is why you see it's a little bit hazy. This is carbon nanotube on surface. This is like same image of the same stuff, different nanotube, of course, but you can see when it's suspended, it's very hard to see. When it's on the surface, you see this like bright image. The setup is very simple. We have like a flow cell that can control the humidity, and you have another setup that can control the humidity, and another setup that can change many environments. The idea was that if you want to do a simultaneous measurement of electrical measurement through the carbon nanotube and EFM measurement, we would like to have everything like to do it in situ. So the idea is that we have like our AFM setup, and we have like 3 electrodes that can go underneath the head of the AFM, the scanner, and then we can study like 2 things. One, the transport of the charge of the current through the carbon nanotube, and to see what happened to the surface near the carbon nanotubes, and to see if we can correlate the 2 things. So this was like the idea. So EFM, there's a lot of research about EFM, a lot of formulas. Because time is quite short, I want to focus on quite a few things. The derivative of the force, you can think about it like the regular electrostatic capacitor, but it creates a lot of terms. This term, like alpha and beta, it really depends on a lot of models. Why there's so many models? Because to model the cantilever interaction with the surface, it's very hard. Even when the surface is metallic, it's not simple. And when the surface is oxide, and maybe on the oxide you have some charge, it's impossible mission. Really, there's many theoretical studies about it. And when you try to use each of these models and to tune it for your own sake, you see that you encounter a lot of problems. And the main issue is that the capacitance and its derivative is hard to model, and model that the tip sample separation, it's very hard to dictate, because when you have charge, it affects the distance between the cantilever and the surface, and it's very hard to know exactly where you are. So what we decided to do, like to use an alternative model or setup. The setup is very simple. Again, you just start with like electrostatic capacitor equation. You must take into account the battery. The battery is very important because you need to find the minimum energy of the system. And you assume, let's say, that you have like a backgate, you have like your silicon O2, you have somewhere a charge, and like they have 2 capacitors between the gate and the surface and the cantilever. And when you use everything together, you come out to the following formula. And when you look at that, you see this is the second derivative of the energy, which is like the first derivative of the force. And you can see there's a lot of terms. and there's no any assumption about this, how the capacitance C0 between the carbon nanotubes and sorry, between the cantilever and the surface is. But what you can see there, beside all these terms, you have a very nice term which is related to, which looks like a potential square. And this potential square, of course, you have the charge, maybe or may not, that exists on the surface. So you look at that, you see like this is df that is z, it's a function of the gate. And instead of looking on the y-axis, which is very, very problematic because it's very hard to model, you look at the x-axis. And the x-axis just tells you exactly how much shift was in Vg minus Vt, and it's related exactly to the Qs. So you can extract Qs, the charge that you would like to see, just by the shift of this parabola. What you need to take, you have like for a given V gate, you take like few V tip, and then you hope to get a very nice parabola, and then you can extract the charge. So this is the idea, which is very similar to what people do in Kelvin probe microscopy, when they try to study the potential surface or the potential work function. So here, for example, just I give you a few examples of how it exists. We take a pristine wafer just from the box, no charge. And then we do like force curve measurement. This is the distance from the surface. This is df to dz. This is really raw data. And what you do, you like take different V tip. And for example, you decided to look at the height at z equal 100, and then you take very nicely, you see the parabola. And from the minimum of the parabola, you can extract the charge, and here you see that the charge practically is 0. You can do more than that. You can just put, instead of Vg equal 0, you can Vg 2 volt. And what happened, you see for different V tip, now the one that costs minimum is different. It's V tip equal 2. So when you plot it again as Vg minus V tip, so you get again the minimum exactly where you expected at Vg or V tip equal 2 volt. So again, you get a very nice parabola, and Qs is really equal 0 because there's no charge. So it's no matter what you do with Vg and V tip, if there's no charge, there's no charge. Because it's an extra charge, not a charge that's related to this capacitance. Okay, so let's see what we can do more. We can take, for example, to do like a ozone plasma. You know that ozone creates some charge. So again, we do the same things, and we get a parabola. And you can extract from the minimum. You see now it's shifted a little bit. You can extract the charge. You can do like oxygen plasma, which is a little bit more robust. And what you can see, you see the movement is a little bit further, and you can extract the charge. And if you compare, for example, this charge divided by charge of the electron, you get like the density. So this is like, 1 10 to 10, 10 to 10 per centimeter square. And here this like 5 10 to 10 per centimeter square. You can see to compare it, for example, with the density of like silicon O2 atoms, which is typically of the order of like, 10 to 15. So you understand that with our sensitivity, like almost 5 orders of magnitude. So it's a tiny charge. It's not all the atoms full with charge. A little bit residual charge that exists because of this process that we can sense. So it's a very, very sensitive setup. And everything is, of course, related to the fact that we have a cantilever with high quality factor, which enable us to sense this. So now let's dive to the carbon nanotubes. This is a carbon nanotube. I, as a function of Vg, you can see here the hysteresis is very big. And when we scan, very, very slow. We increase the scan rate, and you can see how the hysteresis decrease. So you can plot, for example, the hysteresis, like the distance from this point to this point, as a function of the scanning time, and you can see how it behaves very nicely, like some exponential function with some tau. But you can do other stuff. What you can do, you can sit. Instead of scanning, you can sit, and everything is a data. Raw data, the same carbon nanotube, and what you see, you just give a pulses. Like the green is a pulses. You can see like -3 to 0 to 3 to 0, like the green, and you just follow what happened to the nanotube current. And this is, for example, a zoom on one of these, so you can see very nicely how you have this decaying. And apparently what you can see, surprisingly, the decay is almost the same time constant. And the reason is like, it's very simple. What you're doing really, if you do the IV characteristics, or as a function of time, you sense the same phenomena. There's some hysteresis, there's some origin for this hysteresis, and you can sense whatever you like, how you wish. What is important to look in this curve that you can see, beside of this decaying, that always, roughly, it's decayed to the same value of current, and we will return to that. So you can think about this nanotube was on the surface, one of them was suspended, so we can ask ourselves, do we have like a different behavior for carbon nanotube which is on surface or the one which is suspended, okay, just to see. And here, for example, you take a carbon nanotube, this is suspended, you do the same measurement, like pulse measurement, and you take the same carbon nanotube, you stick it to the surface, and you see a little bit the current decrease, but it's really the same. And when you do the same pulse measurement, you get roughly the same time constant. And we have it for other many nanotubes. They're really the same behavior, meaning when the voltage is low, below like 4 volts, the origin of hysteresis for suspended carbon nanotube and on-surface carbon nanotube is the same, which is good. It means that we don't need to, to study this and this. We just need to study one case. You can see, for example, what happened if we take the carbon nanotube, we suspend one and put it in vacuum, there's no hysteresis. Again, on surface, if it's in vacuum, there's no hysteresis. And I'm skip a little bit about some details, but you can change the flow cell, what we did. We changed like to put nitrogen, to put only oxygen without water, to put air, to put water, and at the end you find out that the hysteresis is really depend only in one ingredient of the atmosphere, and this is humidity. So if you have humidity, you will have hysteresis. If you don't have, you will not have. And this was well known, and we just verify that. So here, for example, you see the tau as a function of humidity. And you can see very, very interesting stuff, but when the humidity is quite high, there is some saturation of the time constant. First it decreases, but when the humidity becomes smaller, the time constant increases. Okay, of this decay, and we return to this issue, but this is data, this is fact that we found. So immediately one would like to ask, so where is the water? Okay, this is water, it's very, very important, but where are they? So the catch was the following. When carbon nanotube is suspended, you can run a very high current on the carbon nanotubes, and because it's suspended, it's very hard to take heat from the carbon nanotubes. And the temperature roughly in the middle of the carbon nanotube, when it's far from the electrodes, it's almost, like 70, 80 centigrade. Okay, so it's really, really high. So degrees centigrade. So it means that when you run high current, you will not have any water on the surface of the nanotube because everything is disappeared. And what you can see now, you can see here that while doing this, ramping up the current, we just did exactly the same stuff. So the current, you ramp the current by the bias. But you can still do some IVG, meaning look at the transfer characteristics. And when you do that for different bias, you can see that the hysteresis is still there. For example, if you look at the hysteresis function of VDS, you see that it's roughly the same, almost the same line. Nothing happened to this hysteresis. So this immediately tells you that the water are not on the nanotube, they're somewhere else. What you can do next, you can take the same nanotube and you can heat it on the hot plate. When you heat it on the hot plate, you heat, of course, the suspended nanotube, but also the surface. And then you look at the hysteresis as a function of temperature, you see immediately how it decreases very rapidly to no hysteresis at all. Which immediately tell you that really this water or water layer, if it's really attributed, and we practically sure that it's attributed to this hysteresis, it exists on the surface. So at least one possibility or one thought that people thought before, we believe it was wrong. So now all this is very nice. This is like with the current, the I as a function of time or I as a function of V gate, but we can also study the FM. So what we can do, again, we can have the setup. Now is without any carbon nanotubes, because soon you will understand the model. You'll see that you don't need really the carbon nanotubes. And because you understand that now, if you think about it, if it's happened the same with suspended nanotube and on-surface nanotube, if it's suspended and the water are not on the carbon nanotube, it cannot be that electrons leave the carbon nanotube and cause this hysteresis behavior, because the carbon nanotube is suspended. It cannot, tunnel from the nanotube in air to the surface. So we just need to study this charge. So here you can see an example. You just change again what I just told you. You have a set of electrodes, 2 electrodes. Again, this is the same setup of carbon nanotubes, and you measure dF dz, okay, the derivative of the force as a function of Vg minus Vt, and you can see very nicely how now the curves shifted or are shifted. So you see very nicely how, for example, when Vg is 0, you don't find any charge, but when Vg is positive, you find negative charge, and when Vg is negative, you find positive charge. Okay, so this is like one experiment. Then you can go and study the time dependence. So what you do, you just exactly do these pulses and see what happened at different time. So you just study how the charge, if there is some charge, if this charge is decay. So the idea is the following: there is some charge, and this charge can move on the surface, and if it's moved, we should be able to monitor this charge or this movement. So exactly you can see here the charge as a function of time, and each curve is for different humidity. So you can see here, for example, here the time constant is 36 seconds, and this is like 95, this is like 221. So we can really monitor the movement of charge using this EFM measurement. Exactly as I told you, just put your Vg, specific Vg, and then you take like several V-tip, and you can find the minimum of the parabola, and you can extract the charge. So, and this is the same for just different distances. And the idea is what you field emission, by the way, if somebody is worried about field emission from the electrodes, don't worry about that, we rule it out. And everything is boiled to the fact that it's like a charge redistribution. Okay, charge is moving on the surface. So now this is like the main, I think, cartoon that I can show you, or the main graphs. So it's the following. So now we can really do the simulation measurement. Okay, we measure the time, the current through the carbon nanotube. We measure EFM measurement. Now we would like to combine the two, meaning to do the measurement while sitting near the nanotube and see what happened to the charge. So this is the current as a function of time. This is the charge as a function of time. And you can see here, like, the red is the current data, and the blue is like an exponential fit. Sorry, I forgot what I said. The black I meant. It's a current data, and the blue is the fit, and the red dots is the data of the charge, and the continuous line, this is the fit, exponential fit. So you can see very nicely that here there is a decay when I have Vg minus 2. Then we go to like Vg equal 0. There is like recovery of the charge and the current. Then you go to Vg 2 volt. You have again some recovery and charge, and you can go back to Vg equal 0, and you can see how the decay again. Okay? What's important here to notice is that the current through the carbon nanotube and from the EFM measurement, the charge that we find are correlated completely, meaning they really behave the same. So now we can go to the model. The model is very simple, and after I will present a more detailed model. But the idea is the following. When you have your setup, and which is very different from usual pristine wafer, you have a gate electrode, and you have here like 2 electrodes. So when you apply the voltage between the gate and the electrode, there is the electric field which going from the backgate to the air or to the electrode, but which is let's call it in the z direction or perpendicular direction. But because all these lines should terminate at the electrodes, going to be like some parallel, okay, a component of the electric field on the surface. This electric field, what it would like to do, here in the beginning when Vg is equal 0, always there is some ions that are positive and negative, and they cancel each other sitting on the surface. And when you apply a voltage, what happens that it's better to the system for lowering the energy that the plus is going to screen the electric field that comes from the backgate, and the minuses just stick to the electrodes, okay, just because of the direction of the electric field which exists on the surface, not only perpendicular to the surface. So what happened practically, that this gate is screened by the electric field, by the charge that exists on the surface. So then you can think about it as this is like the simple, very, very simple equation. You have like 2 capacitors. You have like 2 capacitors that exist here and you have some resistance that exists on the surface of the silicon O2. So you can very easily write this kind of equation. You have the current, you have the Ohm's law, and you can relate it to the Gauss law, and all together you get very nicely, as you can see, d rho dt is equal to the charge, and you have some time constant, and this is the time constant. So what this time constant exists? It's 1 over the sigma, the conductivity of the oxide. And the conductivity of the oxide is very, very poor. And this is why these time constants are very long. It's very easy to see that. So of course you can think that this model is too simplified. So you can go and do a very nice COMSOL simulation, and you get, for example, this is like, you can see here the charge as a function of time, and you can see very nicely this is like the red is the experimental result, and the blue is like the fit. And for example, you get a very, very nice agreement between theory and simulation. So it really holds when even you take like a much more detailed model. So how we can understand this hysteresis? Now it's very simple. So the story is the following. Let's start, and this is very, very important because make all this story very, very simple. Let's start at like we start at 1. We start at very negative VG. So very negative VG, you have a lot of electrons here, and you have a lot of holes on the nanotube, and nanotube is a p-type transistor. This is why the current is high. Then you go to point number 2. You go quickly to 0. And when you go quickly to 0, what happens is that you have some charge that accumulates here because of the minus, but you get into the band gap of the carbon nanotube, and this is why you don't have any current. So I write, and it's written here minuses, but practically you are in the band gap. Now, when you're going back to very point 3, very positive gate voltages, this is very, very positive. It starts to accumulate, so the nanotube is really deep in the band gap. It starts to accumulate negative charge. So negative charge starts to accumulate. When you go back, this charge, it's very hard for him because it's moved very, very slowly to leave, to go back, to replace what you did already. And when this charge is very negative, it's like this negative charge. So practically the nanotube, it's on the on state. So what happened is a delay between the charge on the surface to the charge of the gate. And because of this delay, which related exactly to the mobility of the conductivity, or mobility of these ions, and we will talk about who they are in a minute, on the surface of the silicon O2, this is why you have this hysteresis. So there's no 3 minutes? Okay. So this is the model, and now we can, I have 3 minutes, which is a huge amount of time with respect to hysteresis carbon nanotube. So we can go further and ask, does this hysteresis depend on the gate voltages, on how it depends? So, for example, we would like to study if VG affects tau. So what I showed you before, it's when VG, the pulses are quite high, like 2 volt, 3 volt. What happens when VG is very, very small? And you know, in linear response, when J is equal to sigma E, okay, linear response, sigma cannot depend on the voltage, on the electric field. It should be constant. But what we found, you can see very nicely that when VG is small and higher, you can see here, this is again in log-log plot, or log as a function of time, you can see very nicely this like exponential behavior. And when we accumulate all this data, and by the way, the data was accumulated again by the EFM method and by the CNT-based method, meaning it's really very reliable data. You can see here, this is like the result of the data, so it's the following. You can look here. Tau is a function of gate voltage. You can see that when the gate voltage is quite high, you get like a constant tau. But when the gate voltage becomes smaller and smaller, you can see that the tau increases. Meaning, which is very weird, in linear response it cannot be. And you can see the same phenomenon. So this is from the EFM-based measurement, and this is from the CNT-based measurement. So if you put them together, you can see very nicely, and do scaling, you can see very nicely that they're roughly the same data. So there's something very weird here, that the V-gate affect the movement of these ions on the surface or modulate the sigma. So we can look at that in the following way. We showed what we just have, I just showed you is the tau depend on Vg. So when it's very high, it's like constant, and when it's low, there is some increase. I showed you before the tau depend on humidity. So when the humidity is very low, its tau is high. When the humidity is high, tau is low. So we can ask the following. Like A is like B and B is like C, so what would happen between A and C? So it's the following. Vg affect tau, this is the data. Surface water, humidity affect tau, this is the data. So maybe Vg affect the surface water, the humidity. Maybe by playing Vg, I really can modulate the amount of humidity that I have on the surface, the amount of water layer on the surface, which is going to be different from the amount of water that exists on the environment, on our chamber, far from the surface. And everything is by the gate voltage. If this is the case, we can understand exactly why this happened. So we have a very nice model. This model is based on dielectric phoresis. Dielectric phoresis is a very nice setup that instead of taking, if you have a charged molecule, you just need an electric field to take it from place to place. But if it's a neutral, you use the you use a gradient of the electric field. And then because one side is higher than the other side, you can move it from one side to another. Water has a very high dipole moment. So the Vg creates a very nice gradient. The dipole moment of the water really start to fill this Vg and start to accumulate on the surface of your substrate and of your devices. And this depends on Vg. So it's exactly like our atmosphere. So I skip a little bit the details, but you can use like a BET isotherm, and you can find exactly how many layers you have on the surface. And the battle, and after long day, this is what you find. You find that really the combined data is the tau. It really depends on the amount of water layer that exists on the surface. And you can see that when the water layer is about like 2 or 2.5 monolayers of water, like this saturation of this charge movement, but when the amount of a layer is below 2.5, you start to see somehow it's much harder to these ions to move, and this is why tau start to increase. And I think that now I think that I skip the conclusion, because I think that you understood. I will just tell you that what's really interesting is which are these mobile ions. This is something that we study today. This is a new sensing mechanism. Instead, that it's really do integration of this tau and not only like the difference of the current. And you can develop like a hysteresis-free carbon nanotube transistor, and this is something that we already succeed to do. And what is really, really nice is like that what I have showed you, it's like you can use it like to electrochemical switch. Meaning if Vg affect the humidity, and there's a lot of chemical reaction which lead humidity, you can really tune the kinetics of the reaction by the electric field. And finally, I would like to thank my group, and a special thanks. This is really the 4 people that did a marvelous work on this work, and would like to thank very much the MNFU, the nanofabrication unit, for a lot of help, and for you for your attention.